Let us look now to uniform broadcast. So a question that we can raise is the proposed algorithm uniform or not? Remember that uniformity necessitates the following, that if a failed node delivers the message M, then every correct node will deliver the message M. So this is the property of uniformity. So what is the answer to this question? The answer is definitely no. Why is that? Because a sender that starts a uniform broadcast will immediately RB delivers and then crashes. And in this case, it's only that process will deliver the message. To see this, you look here. So when you do a uniform broadcast, you trigger a delivery, an immediate delivery here, and then you perform a BEP broadcast. Assume exactly after this point a crash happens. In this case, there is no guarantee that the BEP broadcast will deliver. Seeing it in another way, you can look at it this way. If here is our process, P, B triggers an RB deliver, and then it triggers a BEP cast, and then here it crashes. Now a BEP cast in itself will trigger a perfect link events, and these events can take any arbitrary time to be delivered to the receivers, and therefore even if a crash happens after the BEP cast, there is no guarantee by the BEP cast to deliver the message to other correct processes. So we have to develop then another algorithm. This is not good enough. So a necessary condition for a uniform delivery is to make sure that all correct processes get the message. So the question now that we have is, how do we know that correct processes got the message? So the way to handle this is the following. We will make the messages pending, waiting, until all correct nodes get it. We collect acknowledgement from this node that got the message. And when we get acknowledgement from all correct processes, then we do the uniform delivery. How to do this? At each node, we have this ACK vector for each message M, and it will contain the set of nodes that have acknowledged the message M. So what can we do? So we'll deliver once all correct processes have ACKed, and we are going to use a perfect failure detector. This algorithm is not that good. It's using a perfect failure detector. But let's assume that for now. And basically, we define the function canDeliver, and canDeliver says it will return true if the set of correct processes are a subset of ACK-M, which is the set that have the processes that have acknowledged the message. As long as all correct processes acknowledge the message, then we can deliver, because then we know that all correct processes will uniformly deliver the message. So here is the algorithm. So when we have a uniform cast event, we add the message to the pending set of messages. We trigger a BEP cast event. Okay, this goes to the BEP component. Whenever we get a delivery from the best ever broadcast, we acknowledge that we have received a message from PI and add it to the set of processes corresponding to these messages. And if the message is not already in the pending set, we add it to the pending set, and then we trigger again a BEP cast. So this is the BEP cast that goes to everybody else. It's only done the first time. The message is not in the pending set. And now the algorithm just ends as follows. If we have a pending message such that we can deliver M, it means what this condition says again, that we received acknowledgement from all correct processes, and it is not delivered, we add it to the delivery set, and then we trigger a uniform deliver. That's as simple as that. So that's what we did. So here we deliver when all correct processes have act. Let us look to an execution scenario where all processes are correct. So this is correct execution scenario. Just to understand this, so here is P1 does a uniform cast. This is a BEP delivery locally of the message from P1. It delivered the message to P2. This BEP delivery, this is the first time it got a BEP delivery of this message. Then it will BEP cast the message. Here it BEP casts also to itself, and BEP casts to other processes. So these are the three things. And here this is delivered. Then when P3 gets a BEP delivery here, it BEP casts the message to, it will also BEP cast to itself. It will BEP cast the message to P2 and P3. Now, if we look to anyone, look to P1, at this point, it has got a BEP delivery from all correct processes, then it uniformly delivers. The same happens here and happens here. This just gives you an idea about the execution of the algorithm. So now let us look to the correctness of this algorithm, the uniform, reliable broadcast. So what do we have? No creation comes from the property of the BEP broadcast. No duplication because we have this deliver set. So now we have two other properties we did not guarantee yet. One is the validity and one is the agreement. Before we go to these two properties, we prove a lemma. And the lemma is as follows. The lemma is saying, if a correct process PI, BEP delivers a message, M, then PI will eventually uniform deliver the message, M. So, if a correct process, BEP deliver, then it will uniform deliver. So let us look how to prove this lemma. Here's the proof. So, a correct process PI, BEP broadcast M as soon as it gets M the first time. So it will BEP cast M. We're talking about correct processes, remember, which implies by the validity of BEP cast, every correct node gets M and also BEP casts M. So every correct node gets M and also BEP casts M, which says that PI itself will get a BEP deliver from every correct node by the property of validity of BEP cast. Now, eventually, can deliver will become true. This is by the completeness of the failure detector, P. P will eventually detect all failed processes, so it will not wait for a failed process forever, okay? And so in this case, can deliver will become true and PI will uniformly deliver. So now we have proved that if a correct process, BEP delivers a message, the correct process will uniformly deliver the message. Good, and you have to remember this. Now, the validity now becomes very easy. The validity is saying, if a sender is correct, then it will eventually uniformly deliver. This is the validity. Okay. So now, if the sender is correct, by the validity of BEP broadcast, it will BEP deliver the message in. And again, if a process which is correct BEP delivers, it will always uniform delivers. So it will eventually then uniform deliver. So if a correct process broadcasts the message, it will eventually uniformly deliver that message. This is the validity condition. Let us now go to the agreement. And now we're talking about uniform agreement. This is interesting, and we have to go it slowly so that understand how to prove it. So remember again, what is the property that we want to prove? We want to prove that if some process, correct or faulty, delivers the message, all correct processes will deliver the message. Assume some process, possibly a failed process, uniformly delivers the message M. This means that can deliver is true. By the accuracy of P, and the accuracy here means that you cannot suspect a correct process, every correct node has BEP delivered, because that's what it means. We now know that every correct process have BEP delivered. Again, from our lemma, because every correct process have BEP delivered, then every correct process will eventually uniformly deliver. So let us look to this, just to explain it one more time. Here it is. Let us look to the execution. So here we assume a process PI. PI uniformly becast a message. PI BEP delivers this message, and then it BEP cast the message. At this point, later on, it gets this event here, which says it can deliver. Then it uniformly deliver the message, but then it crashes. Now, if the failure detector is not accurate, it means it can deliver becomes true even before BEP cast have reached every correct node in the system, because it can suspect a correct node and just says, okay, I can deliver. So if the failure detector is not accurate, there is no guarantee that BEP is delivered to all correct processes. So there is no guarantee that all correct processes uniformly deliver. Okay, thank you.